Smart microcapsules are tiny, engineered structures designed to encapsulate and release substances in response to specific stimuli. These advanced materials have found applications in medicine, material science, and environmental protection, offering controlled release of drugs, self-healing materials, and targeted chemical delivery systems. Unlike conventional microcapsules, which passively release their contents over time, smart microcapsules react dynamically to environmental changes such as temperature, pH, light, or even magnetic and electric fields. How do smart microcapsules work? These microscopic containers consist of an outer shell that protects an inner payload. The shell is designed to respond to external triggers, breaking down, swelling, or becoming permeable when specific conditions are met. This behavior is often achieved by incorporating polymers, lipids, or inorganic nanoparticles that react predictably to external forces. For example, temperature-sensitive microcapsules can remain stable at room temperature but burst open when exposed to body heat, releasing medication precisely when needed. One of the most promising applications of smart microcapsules is in medicine. In drug delivery, these tiny capsules can transport pharmaceuticals through the bloodstream, releasing their active ingredients at the right time and location. Imagine a cancer treatment where chemotherapy drugs are delivered directly to tumor cells. Instead of affecting healthy tissues, scientists have developed pH-repulsed microcapsules that release drugs only in the acidic environment of tumors, reducing side effects and improving treatment effectiveness. Could these capsules change how we take medicine? Traditional pills require the body to absorb and metabolize a drug, leading to fluctuations in concentration. With smart microcapsules, drugs can be released gradually or in response to the body's signals, providing long-lasting and more efficient treatments. For instance, insulin-loaded microcapsules could automatically release insulin in response to blood sugar levels, mimicking the function of the pancreas for diabetic patients. Beyond medicine, these responsive microcapsules are transforming material science. In self-healing materials, capsules containing repair agents are embedded within coatings or polymers. When the material is damaged, the capsules rupture, releasing the repair agents to fill cracks or gaps. This technology is being explored for protective coatings in aerospace, automotive industries, and even electronics, where microcracks could cause circuit failure. How do these capsules respond to non-chemical stimuli? Magnetic and light-sensitive microcapsules offer additional possibilities. Magnetic responsive microcapsules can be guided through the body using external magnetic fields, allowing for targeted drug delivery or imaging applications. Light-activated capsules, on the other hand, can release their contents upon exposure to a specific wavelength of light, making them useful for precise therapeutic treatments such as laser-activated drug release. Could smart microcapsules help the environment? Researchers are exploring biodegradable capsules for controlled pesticide and fertilizer release in agriculture. These capsules could prevent excessive chemical use, reducing environmental contamination while ensuring plants receive nutrients only when needed. Similarly, in water purification, microcapsules filled with reactive agents could selectively trap and neutralize pollutants. The future of smart microcapsules lies in designing even more precise and multifunctional materials. Scientists are developing multi-stimuli-responsive capsules that react to multiple triggers simultaneously, further refining control over their behavior. Could we one day have materials that intelligently adapt to their surroundings, repairing themselves, delivering medicine as needed, and even responding to electronic signals? While these technologies are still evolving, the potential applications of smart microcapsules are vast. From revolutionizing medicine to creating more durable materials and improving environmental sustainability, these tiny structures are reshaping multiple fields of science. What new discoveries will emerge as scientists continue to refine these responsive systems? The possibilities are as small as a microcapsule, but as vast as the future of advanced materials. Smart microcapsules are microscopic structures with a core shell architecture where the shell encloses an active ingredient and releases it in response to specific external stimuli. These capsules can be designed to react to pH changes, temperature variations, light, magnetic fields, or chemical triggers. The responsiveness is achieved by incorporating materials that undergo structural or chemical transformations upon stimulation. This controlled release mechanism makes them highly valuable for targeted drug delivery, self-healing materials, and controlled chemical reactions. pH-sensitive microcapsules can release anti-inflammatory drugs in the stomach but remain sealed in neutral environments. This is like a time-released pill that only dissolves in certain parts of the digestive system. Thermorepester microcapsules release their contents when exposed to specific temperature thresholds, making them useful for hyperthermia-assisted drug delivery. These capsules are often made from polymeric materials that change solubility or permeability when heated. In cancer therapy, localized heating can trigger the release of chemotherapy drugs directly at the tumor site, reducing side effects. The ability to control drug release with precision enhances treatment efficacy and minimizes systemic toxicity. Lipid-based microcapsules release anti-cancer drugs when exposed to temperatures above 40 degC, which is achieved using external infrared lasers. This is similar to a chocolate shell melting only when placed in a warm environment, but staying intact at room temperature. Microcapsules with pH-sensitive polymers are designed to release their contents in environments with a specific pH range, useful in both medicine and material science. In drug delivery, these capsules can protect medications from stomach acid and dissolve in the alkaline intestines for better absorption. In industrial applications, pH-sensitive coatings prevent the premature release of corrosion inhibitors or catalysts in neutral conditions. Such designs improve drug bioavailability and enhance material longevity. Oral insulin formulations use pH-responsive microcapsules to ensure insulin is only released in the intestines, avoiding breakdown by stomach acid. This is like a soap bubble bursting only in soapy water but remaining intact in clean water. Light, simply microcapsules utilize photoreproducing materials such as azobenzene derivatives or gold nanoparticles that change structure upon exposure to UV or near-infrared NIR light. These capsules allow spatial and temporal control of cargo release, particularly useful in targeted therapies and remote-controlled chemical reactions. In medicine, they enable non-invasive drug activation by applying light to specific areas of the body. Light-activated microcapsules are also used in self-healing coatings and dynamic materials. Gold nanoparticle microcapsules release drugs when exposed to near-infrared laser pulses, allowing precise treatment in deep tissues. This is like a sealed container opening when exposed to a flashlight, but staying closed in the dark. Magnetically responsive microcapsules contain iron oxide nanoparticles or similar ferromagnetic materials that react to external magnetic fields. They are used for magnetic drug targeting, where an external magnet directs the capsules to specific sites in the body. Additionally, these capsules can be heated using alternating magnetic fields, triggering controlled drug release or reaction activation. Industrial applications include self-healing coatings and magnetically controlled lubricants. Magnetic microcapsules injected into blood vessels can be guided by an external magnet to target tumors directly. This is like a tiny boat being steered in a pond using a magnet instead of a paddle. Smart microcapsules embedded in self-healing materials release healing agents when cracks form in coatings or polymers. These capsules rupture in response to mechanical stress, temperature changes, or humidity, filling cracks and preventing material failure. Such applications enhance the durability of coatings, electronics, and structural materials. The integration of self-repairing microcapsules reduces maintenance costs and extends the lifespan of engineered surfaces. Polyurethane coatings with micro-encapsulated epoxy resins autonomously repair cracks in car paints, preventing corrosion. This is like a wound healing itself when skin cells regenerate after an injury. In the food industry, microcapsules are used to protect sensitive ingredients like probiotics, vitamins, and flavors from degradation. These microcapsules release nutrients when exposed to specific conditions such as stomach acid, moisture, or heat. In agriculture, microcapsules encapsulate pesticides or fertilizers, ensuring a controlled release over time rather than an immediate burst. This approach improves nutrient absorption, extends shelf life, and minimizes environmental impact. Encapsulated probiotics in yogurt remain dormant until they reach the intestines where they are most effective. This is like a seed remaining dormant until soil, moisture, and temperature trigger germination. In cosmetics, microcapsules enhance the stability, penetration, and release of active ingredients such as retinol, vitamin C, and essential oils. These capsules prevent premature oxidation and ensure that ingredients are only released when applied to the skin. Some skincare formulations use pressure-sensitive microcapsules that release moisturizers upon rubbing or massaging. This technology improves the effectiveness of anti-aging, sun protection, and fragrance delivery systems. Anti-aging serums use microcapsules to stabilize retinol and release it gradually over time, reducing irritation. This is like a perfume bottle that only releases fragrance when pressed, preventing it from evaporating too soon. The next generation of smart microcapsules focuses on multi-stimuli responsiveness, where a single capsule reacts to multiple triggers such as pH, temperature, and light simultaneously. Researchers are exploring biodegradable microcapsules to reduce environmental impact and develop responsive delivery systems for precision medicine. Additionally, advancements in 3D printing and nanotechnology are enabling custom-designed microcapsules with tailored release mechanisms. These innovations will revolutionize targeted drug delivery, materials science, and smart packaging. Next-generation microcapsules in cancer therapy will only release drugs when they detect both acidity and heat from tumor environments. This is like a smart lock that only opens when it recognizes the correct fingerprint and temperature.